Welcome to chapter 20. In this chapter, we'll discuss the details of the Linux operating system. So, this will primarily draw on whatever has been taught in the first 19 chapters. So, we will only look at a practical realization of the same. So, the outline of the chapter is like this. We will look at the history of Linux, the design principles. Definitely look at something which is very important and very kernel specific to Linux kernel modules. Then look at the usual process management and scheduling, memory management, file systems, input output. So that covers the role of the OS as the memory and the IO manager. Then, of course, look at the communication aspects, both inter-process as well as network based. And finally, we shall take a brief look at the security of the Linux operating system. So the objectives here again are the same, to explore how the Unix operating system thrived and how that led to the design of Linux, to look at the process model and the memory management systems of Linux, and then see how Linux implements both file systems as well as IO managers, IO management systems or IO device drivers, whatever you may call. So the history is like this. Linux is a modern operating system, which is a very unique pedigree in the sense that long back this dates this predates the internet. There used to be an OS called Minix. So Minix was an academic operating system. So the entire idea, so initially Linus Torvalds, who was a student in Finland, he wanted to extend Minix and create something. So of course then he did that, and gradually it became a new kernel, and that is how Linux was born. And because Unix was the predominant operating system those days, so Windows was still not all that popular. One of the main aims was Unix compatibility, which was kind of there by design. So, what he did is that he leveraged the power of the internet and released the code as open source code. Henceforth, the history has been very interesting in the sense there have been a lot of collaborations, so the entire development has been collaborative. It has been over the internet. So pretty much a lot of people saw this, OS coming up on the net. They were able to contribute. The licensing allowed them to contribute. They were given their, due respect and due credit. Gradually, it grew. So starting from a pure PC operating system, it grew to encompass servers. So in fact, most of the servers in my research group run on Linux. And nowadays, it covers everything, starting from small embedded devices to smartwatches to large servers, supercomputers. Linux is there everywhere. The core part of the operating system is the kernel, which is entirely new, but also a large part of Linux has been influenced by the Unix operating systems to various extents, right? And of course, much of the code that runs on traditional Unix, which is third party code, also runs on Linux with very little modifications. What different Linux distributions such as Ubuntu, Red Hat, and so on, what they basically differ in is essentially small parts of the kernel, not much, but mostly the applications that they offer and the management tools. Most notably, the device drivers and the package manager. This is where they actually differ in the way that the system is configured. But the basic core or the kernel remains the same, even though there may be minor modifications here and there. So the Linux kernel, as we have discussed, started version 0.01 was released in 1991. Initially, it didn't have networking because you didn't have to. So those days, networking was not a prereq. It was initially tailored for the 80386 compatible Intel processors running on PC hardware. Very limited device support. In fact, this is a problem that has plagued Linux for quite some time. And mostly it supported the Minix file system because that is what it grew from. But gradually, with Linux 1.0, new features started coming in. So here again, it was influenced quite a bit by the free Unix that was available those days, the BSD Berkeley standard Unix. So there was support for the Unix's standard TCP/IP networking. There was a Unix compatible socket interface for network programming, device driver support for running IP over an Ethernet uh, connection. So these were, mind you, the very early days of the internet. So that is why TCP/IP and Ethernet were still futuristic technologies. The Linux file systems gradually came into shape at this time, including support for the SCSI hard drives, which are the more expensive hard drives, as opposed to IDE and SATA hard drives. So, with all of this, till version 1.2, it remained a PC only kernel, but gradually it started moving into servers. And then it moved on to embedded devices and smaller devices. So, the Linux kernels, the version number indicates whether it is a stable kernel or a development kernel. So, let's look at, let's say, version 2.4. So version 2.4 is stable. So whatever new features will come, they will go into the development kernel, which is 2.5. And once they sort of become stable, they are moved into a stable branch, which is 2.6. So Linux version numbers have been increasing in this fashion, and this has been the development of Linux ever since its inception. So then in June 1996, 2.0 added a few new capabilities in the sense that it started supporting the DEC alpha architecture, which was again the predominant server architecture those days, and support for multiprocessor routines also came in. The other new features that were included was, so mind you, given the fact that Linux now became a server operating system, improved memory management, TCP/IP, and the kernel itself became multi-threaded. So there was support for internal kernel threads and kernel modules. So this is something that we will discuss. So pretty much the idea was that we have a kernel, and then we have, you know, let's say for a large number of devices and features, instead of having all the code within the kernel, you have loadable modules. On demand, something quite similar to DLLs, these modules can be loaded into the kernel. And of course, there are strict, security gates at both ends. But the key point is that in spite of the security barrier, the module would still count as regular kernel code, and the module and the kernel together could kind of become the new kernel with enhanced features. So modules were used mostly for device drivers and other features that involved IO devices at the beginning. But nowadays, of course, modules have become commonplace. So many a time, especially for some advanced support with either the file system or networking, modules are used. So then gradually Linux got it was ported for more processors like the Motorola processors, which used to go into the Apple Apple machines those days, SunSpark, PowerPC, and so on. So 2.4 and 2.6 were in a certain sense very iconic kernel versions. So they increased multiprocessor support, added new kinds of file systems, for example, the journaling file system that we have looked at. The kernel itself became preemptive in the sense that kernel threads, of course, had been there for a long time, but they were non preemptive. But sometimes, for providing better timing guarantees, it became a better idea to have a preemptive kernel. Also, given the fact that we had servers with a lot of memory, 64-bit memory support was required. On the 20th anniversary of Linux, version 3 was released, which had even better support for some newer features like virtualization and, of course, better memory management. And the task scheduler that Linux is really known for, which we have also covered, the CFS scheduler or the completely fair scheduler, that was built and released as a part of Linux version 3. So then, of course, we have moved to Linux version 4 and 5 and so on. But we are looking at some of the very key features or some of the most iconic features of Linux that differentiate it from other operating systems. So Linux is kind of a part of an the free software ecosystem, and the other important entity in the free software ecosystem is Berkeley's BSD operating system. And another interesting thing that was done in Linux, which of course other operating systems emulated much later, was that the kernel did not have a graphical interface. The graphical interface was separate. It was known as the X window system, which allowed us to do amazing things in the sense that the first time I used Linux, the code was running on some machine, but the display was being sent to some other machine. All thanks to the X window system developed by MIT that pretty much decoupled the execution of the kernel and the display, which meant that the kernel can run on the server, but the display can happen on the local machine. And also because of the free software's GNU, or also called the GNU project, a large number of libraries, particularly the C libraries, and a lot of code, a lot of applications. So all the applications that we use, GCC, Vim, and Emacs, and so on, came from the GNU project. Many of the network administration tools were derived from the BSD code. So in fact, the BSD code formed the base for the networking module in Linux. And also, many recent BSD derivatives have borrowed some concepts from Linux. So it has been it's like a two-way street. The fantastic thing is that, of course, Linus Torvalds, he is the overall coordinator, but Linux is still maintained by a very loose group of developers all over the world, right? All over the internet. So they are there everywhere and they collaborate. So they have a strict, sense of quality control, but they collaborate and then they build these systems. So Linux has contributed in many ways to standards. So it has the file system hierarchy standard, which specifies the overall layout of a standard file system in Linux, which has become a standard, across other Unix-like operating systems as well. And you would also find some, rudimentary support for dealing with such file systems in Windows as well. So Linux has been quite iconic in the development of open source and freely usable operating systems. This is not something that can be ignored. So that is why we decided to start with Linux. Also, as is typical in most operating systems courses, most of the assignments are Linux based. So, coming to the Linux distributions, so as we have said, the kernel being mostly the same, what is actually distributed is a precompiled set of packages. So, packages means packages of software packages. So, they would include the basic Linux system, the kernel, the shells, terminals, system installation and management utilities, and other ready to install packages of common Unix tools, which are kind of common across the entire Unix world, such as sed, org, grep, and even VI, Vim, Emacs, and so on. So the first few package managers used to just unzip the files, but of course, after that, things have gotten or they have become much better. So we have distributions like Red Hat and Debian. Red Hat particularly also became a very successful commercial company. As of now, IBM has acquired it. And then, of course, we had very successful free versions of Linux, such as Canonical and SUSE. So, in terms of package files, two formats became extremely popular: the Red Hat Package Manager (RPM), which others operating systems also support, and the Debian Package Manager, which is part of the Ubuntu Linux versions. So, they are also very, very popular. So both of them, they essentially what they do is they bundle the code, the code mostly in compiled form, object form, and along with that they have a list of dependencies with other libraries, right, which are installed in the system. And of course, if they are not installed, and when we try to download one such package, we are given an option with regards to whether we would like to install a certain library or not. But most of the time, it does the installation on its own. So all of these dependencies, particularly application library and library dependencies, it is the job of the package manager to figure out, unless we don't want a library to be installed. Another very important thing is the licensing of Linux. So this actually the licensing has good and bad parts. I'll explain both. So the kernel is distributed under the GNU General Public License. So that itself as of today has three versions, V1, V2 and V3. So it's important to understand that all rights are not waived in the sense if I use a product such as Linux which is licensed under a GNU license, right? And then I create a derived product out of it, then I cannot just distribute the derived product. So this is something that I cannot do. Even if I distribute it, I'll have to distribute it and I'll also have to provide the source code. In the sense, if I'm taking something from the community, I'll have to give it back to the community. So that is why I cannot really create a closed source proprietary form of the code. So the source code is something which must be given. So given that, so this is the good part, but the bad part is that many times many people or many companies decide not to use Linux and instead go for BSD Unix, mainly because they don't want to release their source code. So this again, Linux has grown because of the GNU license. Otherwise, nobody would have had an incentive to actually contribute to Linux. But again, this also limits its use. So Linux, as we have discussed, if I were to go through the design principles, it's a modern multi-user multitasking system which tries to be Unix compatible. Its file system does adhere to the traditional Unix semantics, right? Which is essentially the last writer wins, and a few more things. If you close the file, the entire changes are persisted to the disk. It is fully compliant with the Unix networking model because much of its code is derived from Unix. And like other operating systems, I won't say it is specific to Linux, the goals are speed, efficiency, and standardization. So Linux is designed to be POSIX compliant. So POSIX is an international standard. So Unix is also compliant with it, and large parts of Windows are also compliant. So Linux is designed to be POSIX compliant. So it does support many things which are a part of the POSIX standards. That includes subset support for P threads, which are POSIX threads, support for POSIX real-time processes, and so on. The programming interface of Linux, and in fact with the terminal and shell and so on, are quite compatible to the yesteryear Unixes because that was an explicit design aim ever since Linux was conceptualized. So the components of a Linux system are like this. We have loadable kernel modules and the kernel. Then we have shared libraries in the system which all programs can use. So these are known as standard libraries or stdlib. You will find them in user lib or user bin lib or so on. And then there are a set of programs that Linux itself provides, which are system management programs. Then we have a bunch of user utility programs like sed and awk and grep and ls and so on. The most important programs in the user space are the user processes themselves and compilers, right? So they are compilers are distinguished in the sense that they help us create more code. And then of course we have user processes which we can either compile on a local system or we can get them from a server. So let us now look at the key components of a Linux system. So Linux has three main bodies of the code. So the most important is of course the kernel. So the kernel maintains not only maintains the most important abstractions and provides the interface, but also it executes the core of the operating system, which is known as the kernel code. And needless to say, this also executes within kernel mode. In this mode, it has all access to the privilege modes of the CPU and the machine. All the kernel, all the kernel code and data structures are kept in the same address space or are kept in the same single address space, which is accessible to the kernel and typically not to the Well, not typically, but it's not accessible to the user mode programs. So in 32-bit systems, what is normally done is that the lower 3 GBs of the virtual address space are given to the user programs and the upper 1 GB is given to the kernel. And so there are several advantages of also why the virtual address space needs to be split. So one key reason is that even at the virtual address level, we will know which one is the kernel address and which one is the user mode address. So that will help us address security concerns. The other is that if, let's say, the addresses do not overlap, we need not flush the TLB when there is a context switch from the user mode to the kernel mode. So these are the main reasons why we do this. The other components are the system libraries and the system utilities. So the system libraries are essentially encapsulate the code for system calls. So if let's say I'm making a system call, so that would involve setting the values of registers, setting the values of addresses in the stack. Most of this is done with dedicated assembly routines. So there is a need to encapsulate them in a nice user level API in either C, C++, Java. So these will be basically a standard set of functions which will interact with the kernel, but they need a nice encapsulation such that user code can easily call these. So for example, the printf and scanf functions in C are examples of uh, such pieces of code where these are distributed as regular library routines. Along with that, we have system utilities which perform specialized management tasks. And so the system utilities, for example, the cron daemons in Linux, which periodically run certain tasks, something similar to that. And then, of course, we have the user level programs, which are typically launched via a shell, like for example, Bash. So they are quite rich and varied. So they form the last component of the full Linux ecosystem. So now let us discuss kernel modules. So these are sections of the kernel code which are pretty much like the way DLLs are structured for regular code in the sense that we will boot with a simple bare bones kernel and then dynamically at runtime we can load a module into the kernel. So this will allow us to extend the functionalities of the kernel. For example, kernel modules can be used to implement device drivers. So if you think about it, we can have thousands of devices, right? It would be quite impractical to include all their device drivers as a part of the kernel module, and device drivers have to run in the kernel context. So that is why what we can do is we can include a device driver uh, as a module which can be loaded as and when the device is plugged in. Something similar holds for a file system or a networking protocol. So it makes little sense to have kernel code for all of these things all inbuilt. The kernel will then become massive. So it's a much better idea to have these as modules and load them on demand. Furthermore, the module interface will allow third parties to write their own modules, which can be distributed. And furthermore, they are not under the GNU public licensing umbrella. So what they can do is they can write proprietary source code for their device drivers and file systems. So there is, in principle, no need or no real need to actually include the source code of to open source the source code of these modules, right? So there is also a legal reason for why modules are important. Other than that, of course, the kernel size remains small and minimal, right? So these are also known as a microkernel based design. So let's now look at some of the main So some of the primary methods or the components the Linux kernel modules support. So Linux kernel modules are also known as LKMs. And if you want to Google, you should Google for the mod probe command, which helps us do many of these module related actions. So there is a module management system. Then we have loaders and unloaders, a driver registration system, and a conflict resolution mechanism. So in module management, the key point is loading of the modules into the kernel memory. So this is quite similar to the way that we actually load dynamically linked libraries or DLLs into the memory of applications. And furthermore, the module management also takes care of how they will talk to the rest of the kernel, quite similar to DLLs. The module loading in itself is split into different parts. So first is that the code of the module has to be inserted into the code base of the kernel, which means that in the virtual address space of the code of the kernel, there need to be sufficiently large holes where the codes of the module can go in. Second, we need to export all the functions that the module is providing such that the other kernel functions can use them. So we'll talk more about this in the module registration part. And we also should need to look at what exactly within the kernel in terms of functions and variables this module can access. So we are well advised to limit the scope of modules such that they cannot access the entire kernel. So the module requester would of course call the module manager to load the module, and it will also regularly query the kernel to find out whether the module is loaded unloaded, and the kernel will also unload modules to as and when they are required, or this can also be done quite explicitly using a command to unload a module. So in terms of driver registration, so the key point is that assume I have a machine and then I plug in a USB device. So the moment I plug in a USB device, the driver is required. So for many USB devices, a driver is required. So the job of the kernel is to search for drivers and load them. So it is important to tell the rest of the kernel that look, a module has been loaded which contains a driver for a certain device, and what is actually required is that to interact with the device we need a standard interface, which of course should be there, which of course the driver should implement. But along with that, the kernel will maintain a driver registration table, let's call it a DRT table, where given a certain device, there will be a pointer to its driver. So the pointer could just be a pointer to maybe the starting memory address of the driver, or some other handle that will allow us to locate the driver code and the functions that the driver provides at runtime. So this registration table will of course include the device drivers as we have just seen, but we could also have similar registration tables for other kinds of modules. For example, we could have one for file systems where if let's say we are entering into a part of the directory which is not a regular kernel file system but something that we have loaded, then the appropriate file system driver will be called. And this again can be managed via a table where we basically store the mount points. Essentially, this would be the mount point, and this will tell us which file system driver we need to access. Something quite similar holds for network protocols as well as the format of a binary. So, what exactly is the format of a binary? Well, if we consider executable files in Linux, then they have a certain format. So, the most common format is the ELF format. But of course, you could have many more kinds of formats. But the ELF format is the one that has default support. So in this case, the first few bytes are known as magic numbers. Then we have a text section and then data, BSS, heap. So as we have seen, so sorry, not heap. We have the text section, which is the code. And then of course, we mention all the variables which are initialized, right? The data section. and some more information about what exactly are the library dependencies of this executable. So of course, if we change the format, we can always compile a executable in a different format. In this case, we would need specialized kernel support to actually run it. And this is where again modules come into play, where if the format is specified, then the kernel can look up a table and load appropriate code from the appropriate module to handle the binary. So at runtime, essentially modules register themselves by making entries in these tables. And when we deregister a module, we remove the entry, we remove the row. We could, of course, have conflicts where different device drivers would try to access the same hardware, reserve the same hardware resources, or even it is possible that one device driver may set the hardware to a certain state, and and this may cause a problem with another device driver. So this is why conflict resolution, particularly at the hardware level, incidentally the same can happen in the software level as well, needs to be done. So we have to prevent modules from clashing over access to hardware resources. We have to prevent the autoprobe. So autoprobes are the kernel daemons that probe device drivers and remove them if they're not being used. So we need to stop them from interfering with existing device drivers. And furthermore, we need to resolve conflicts when multiple drivers are trying to access the same hardware, right? So this means that the kernel needs to maintain a list of allocated hardware resources, all the hardware resources that have been allocated. They need to be there with the kernel and also which module is using what. Before actually using a set of using hardware, a driver has to request for the resource and it needs to get explicitly allocated to it. Only then will a driver be able to use it. And if, let's say, such reservation requests are rejected, in the sense that if a resource is not available, right, in the sense another driver is using, then such requests are rejected, which means that the driver module will try later. So let us now look at move into another aspect, which is process management. So Unix process management separates the creation of processes into two distinct operations, as we have seen. So essentially, one process runs, which is the parent process, and the entire process of this happening starts from the init process. But the key idea is we have a parent, then the parent forks off a child. This is done by the fork system call. And of course, there are now generalized avatars of the fork system call in terms of the clone system call. So once a child has been created, it can create a new image, in the sense it can load a new binary on its existing space using the exec system call. So the fork and exec is the quintessential Linux mechanism for actually creating a new process. And under Unix and also under Linux, the process needs to encompass the process. Every process will have a process data structure. We'll see what that looks like. But that needs to track the entire context of a process, right? So what exactly is there? The properties of a process in Linux will include the processor's identity. So every process has a unique ID. This is maintained. The environment in which the process operates in. So we will look more into this, and also the context, right? So we will look at these three things. So for a given process, what we actually maintain are three things. One is its ID information, second is its environment information, and third is its context information. So at the OS level, we have to maintain these three unique pieces of data for each process. So under Linux, every process has a unique identity, and the identity itself contains many parts. So the first is, of course, the process ID or the PID, which we can get from the get PID system call, which will give you the PID of the currently executing process. So this uniquely identifies the process to the rest of the kernel in the sense we can use this PID to signal a waiting process, modify its execution in some way, or wait for it. Along with that, along with a unique identifier in terms of the user, a process also has other credentials in terms of the user ID, the user who has spawned the process, the effective user ID, the permissions that the process has. The user ID and the effective user ID may be different. So we have already seen some cases of that. And furthermore, a process may inherit the credentials or the permissions from different groups. So it may technically have different group IDs, which will allow it to access different system resources and different files. One more new thing, which is a very rarely used feature in Linux, and many a time we don't even hear about it, is the personality of a process. So, as I have said, a key design goal of Linux was to be compatible with Unix. But given the fact that there are different flavors of Unix, the behavior of the kernel should slightly vary to basically capture that, to capture the fact that a processor is actually operating with different flavors of Unix, right? So this is why this is called the personality, where the semantics of the system calls can vary slightly depending upon which flavor of Unix you would like to emulate. One more new and very exciting feature of Linux is the notion of this namespace. So, namespace basically refers to a specific view of the file system hierarchy in the sense that all the accesses need not, all the processes need not see the file system to begin at slash, right, which is the root hierarchy, which is the root level file system in Linux. They can look at a much smaller part of the file system, right? So for them, the file system could be a much smaller part. So this, of course, is done for unique security reasons, and they may see their root, so their virtual root, which they will still read as slash, may be actually a very small subset of the file system. So this is known as a namespace, right? Which is a unique file system hierarchy with its own root directory for a given process. So this, of course, has to be separately set. Then comes the process environment, also known as ENV. So in Unix, or even in Windows, and even in DOS and everywhere else, there are environment variables. So some important environment variables, for example, are $home indicates the home directory, $path indicates the locations of all the directories where you will actually search for executables, right? So let's say that you want to execute a command, you will search for all the directories in the path. Similarly, there is something called LD library path, which is where you will search for all your libraries, right? Particularly all your dynamic libraries that you need to load. So the environment of a process, which is essentially all of its environment variables that in a sense influence its behavior, are inherited from the parent, but of course they're also inherited from the shell. And the environment means many things. So first is an argument vector that looks at all the command line arguments used to invoke a running program, so the argument and the value. Then we have the environment vector, which is a list of name value pairs as we have seen, where the name is the name of the environment variable like home and path and LD library path and so on. And the value is the values that they actually take. So this is a very flexible means of processing, and other than the argument, the environment is something that a process actually inherits from its parent, and many a time the parent is the shell process, so you inherit the environment of the shell. So this is how the execution of a process can be configured, in the sense that, well, of course, like variables like the path and LD library path indicate, tell us how it will behave in terms of executing other programs and loading libraries and so on. But many a time it also looks at specialized environment variables which are application specific to see what it needs to do. For example, let's say that it needs to read a configuration file from some place. That configuration file, the location of that could be specified via an environment variable, which the process can read. So, in that sense, the process's environment is indeed being set via these variables, and that is influencing the behavior of the process when it's running. Now, let's come to the third part, which is the process context. This is something which is explicitly stored uh, upon a context switch, right? So, that is also why this word has come about, the context switch. So, the context itself contains a lot of things. So, one of them is the scheduling context. It is the important information that is needed to suspend and restart the process. So basically, we have already seen what the scheduling context would have, in the sense it would have the last executed PC, the view of all the registers, and if let's say value of the flags of hardware, right? For some hardware units, if certain flags have been set, they will also be a part of the context. So this is by far the most important, because this is what we need to read upon a context switch and then again restore. The kernel maintains accounting information about all the resources that a process is accessing. This would include file system resources, network resources, hardware resources, IO resources. So, this is also a part of the context, but of course, it is not as important as the scheduling context. Then, of course, there is a file table. So, in the file table, what happens is that typically when a process opens a file, it is given a file descriptor. The file descriptor then is used to actually, it's a handle to the actual file, which is nothing but a much larger data structure, which contains disk level information of where each block is and so on. So that data structure is known as the inode, which is something that we have seen earlier. But given the fact that we don't really want to give inode pointers to regular processes, what we do is that we give it simple integer IDs that is used to index the file table. And the file table of a process is also a part of its context. So a process could have many other tables for network connections and so on. But clearly, the scheduling context is the most important component per se of the process context. But then again, you have these additional tables as well. So then, what else does the process context contain? It also contains a file system context, which has the details of open files, the current root and default directories, right? So basically, this is used if you are using a namespace, which will tell you that look where exactly your root starts. Then, of course, we could have other things like a signal handler table, which is basically, if you would go back to our discussion on signals, so we can register a table with the kernel, which is actually stored as a part of the processor's context, where we tell it that look, if this signal arrives, and there are not many signals, there are only 20 or 30 different kinds of signals. So if this signal arrives, you call this function within the processor's address space. So the table will essentially contain function pointers into the processor's address space, and it will contain so it will be indexed by the signal, the number of the signal. And then we'll have a virtual memory context which will describe the full contents of the private address space. It is not the full memory, but it essentially describes some key attributes of the virtual memory. So this is not stored or retrieved, even though you may consider all the memory that a process owns as a part of its context. But again, this is not something which is, you only have pointers to all the page tables and so on. You may want to consider page tables as a part of the context, but nothing more than that. Now, coming to processes and threads. So, internally, Linux uses the same representation for both processes as well as threads. A thread is is an example of a context in the sense that Linux generalizes both and calls them tasks. A process is a special kind of task where there is no sharing, and a thread is a special kind of task where large parts of the code and data sections are shared. What is not shared is essentially the PC, the registers, and the stack. Registers meaning the view of registers and the stack. Furthermore, a distinction is made when a thread is created. So we typically use the fork to create a task, which is a process, and we use the clone system call to create a new task nonetheless with its own identity, but it is allowed to share memory structures with its parent. And the clone system call itself has different flags indicating what it shares with its parent. So clone fs means the file system is shared, clone vm means the memory space is shared. So these are essentially bits in a bit vector. So based on the bits that we set to 1, the relevant aspect will get cloned. So similarly, clone sig hand indicates whether the signal handlers are shared, and clone files indicates whether the set of open files is shared. So now coming to the scheduling. So the job of allocating the CPU to different tasks within an operating system, as we have seen, is the role of the scheduler, right? So whenever we run a kernel task, this will involve running the tasks that the system call requires and also running other independent bookkeeping tasks which are internal to the kernel. So typically what happens is that if I have a user program and it makes a system call and we go to the kernel, so then this is registered with the kernel thread that corresponds to the user thread. So as we have discussed, there is always a twin kernel thread that is twinned paired with the user thread. So the kernel does schedule that, but also because the kernel has the control, it also uses this opportunity to do some work of its own. After doing all of that, it resumes the application process or the user mode process. So as of 2.5, there was a preemptive priority based scheduling algorithm, but the current version of the CFS is the completely fair scheduler, which we have also discussed in previous slides. This was introduced as a version 2.6, which takes into account different kinds of classes very well. And if you would recall, the key idea was that we divide time into large quanta, and based on the priority of a task, it needs to at least execute once within that time quantum. So, just to elaborate on that, in a CFS, we don't have the traditional idea of a time slice, but what happens is that we, based on a processor's priority and also other attributes, it is allocated a portion of the processor's time. So, as a function of the number of tasks and the relative priorities, CFS calculates how long a process should run. If there are n runnable tasks, for instance, with the same priority, each gets 1 by n of the processor time. And we can further increase or decrease the priority based on the nice value. So, if you would recall, the nice value can be used in a non-super user mode to reduce the priority, and in super user mode to increase the priority. But in any case, the priority of a user mode process will never be that of a real time process. But in any case, that doesn't matter. The key point is based on priorities and so on, we arrive at a formula which basically tells us that look, you need to execute for X percentage of time. So when we define a large time quantum, what CFS guarantees, which we call completely fair, is that at least for X percent, this task will run. Right? We can't say when exactly it will run, but within this time quantum, it is guaranteed to run for X percent. So this is pretty much the way that the Linux scheduling algorithm works. Right. So basically, if I were to elaborate slightly further, so what we do is we look at a task's weight and we divide it by the weight of all runnable tasks. So that provides us with some, that provides us with this percentage X, right, for how long it should run. And we define this large time quanta. This is also known as the target latency. It doesn't matter. But within this, the task should run at least once and with this proportion. So if there are two runnable tasks, and the target latency is 10 milliseconds, then each of them needs to run for 5 milliseconds. So we don't really care at the high level how exactly they run. So they could be context switching at the level of 1 millisecond, then 1 millisecond, and so on. But much of this would actually depend upon the nature of the tasks and what kind of scheduling strategy is employed. And this would also take inputs from the user in the sense that the user says that this is of a more interactive nature, then we will switch more often, otherwise we will not. Because even switching involves an overhead. So what exactly are the overheads of a context switch? So the overheads of a context switch are like this. So one is of course the time. So this includes the time that it goes in kernel mode to save the context, restore and run the scheduler. The second is kernel may do its own work because since you're going to the kernel, it can opportunistically do more of its work. And then, of course, is the issue of cache misses in the sense that when the new task comes up, it will find that its TLB and cache is mostly populated with entries from the previous task, and this will cause cache misses. So, this is why context switches are quite expensive and we need to avoid. So, with regards to kernel synchronization, it is possible that running programs, device drivers, and so on may access the same kernel data structure. So I'm talking of a software data structure. We could also have a software data structure to protect a given piece of hardware that would still amount to the same idea. So this means that we need synchronization within the kernel. So Linux uses two techniques. One is the old method and one is a newer method. So the older method was that, so this was primarily for uniprocessor systems, okay? So this was like long back. So what happened is that if let's say the kernel was executing some piece of code, then we would make that piece of code non-interruptible. In the sense, no interrupt can come in the middle. As a result, there is simply no way that another task could execute the same kernel code. So the kernel started, it will finish over here. So mind you, since we are assuming a uniprocessor, there is no problem because once you start, you will have to end here. So even if a hardware interrupt comes, nothing, it just gets queued, right? It gets queued in hardware. But the second technique, which is more common, is like this that we look at both single processors and multiprocessors and we use a variety of approaches. So, on a single processor, for a short duration, we can actually disable interrupts. The advantage of that is that nothing else can run. The kernel code would continue to run because even the timer interrupt will not get serviced. So, whatever you started, you will run. There is nobody to interrupt you. But the moment we consider multiple processors, this abstraction breaks because even if we disable interrupts on one core, right, it is possible that a thread running on another core will also be running in kernel mode and that may modify the data structure, which will lead to a race condition. And that is why you would need to use similar data structures used in synchronization like locks and unlocks and also other things that we have seen like semaphores and reader writer locks and so on also to protect kernel data structures, right? So we cannot escape from that. Of course, for the kernel, we have one option which is not available to user programs, which is to enable and disable interrupts. So this will make the kernel non-preemptible for that period. For uniprocessors, it is a good idea, even though the responsiveness of IO operations decrease. But the moment we have multiple processors, we have to use the software versions of synchronization, which we have looked at in great detail. So, to avoid performance penalties, the idea is you want to minimize the time in which your interrupts are disabled or the time in which the kernel is non preemptible. This time has to be minimized. Otherwise, what will happen is interrupts will just queue up, and then you will have issues with, high throughput hardware like network cards and so on. So, one good approach is that we divide important pieces of kernel code, such as interrupt service routines, which are very sensitive, into two parts: the top half and the bottom half. The top half is something you have to do immediately to service the interrupt. So, this part typically runs with interrupts disabled. And furthermore, the top half is you're not supposed to access any data structure that requires any kind of synchronization. Otherwise, if let's say this part is waiting to get a lock, it may wait there forever and the kernel will just hang. So that is why the top half is not allowed to actually access synchronization operations, and it runs with interrupts disabled. The bottom half, on the other hand, is where a bulk of the processing happens, and this can happen much later after the immediate requirements have been taken care of. So in this case, the interrupts are enabled, in the sense the bottom halves are also often preemptible. You just don't want the bottom halves to again raise interrupts or do something to interrupt themselves. So there are certain subtle correctness issues with bottom halves. So this is better discussed in a more advanced course on operating systems. But by and large, bottom halves are like regular kernel tasks which don't disable interrupts. So the architecture will be completed when, let's say, you disable a few bottom halves while executing normal foreground kernel code, because the reason being that bottom halves also tend to interact with the hardware and also generate interrupts and so on. So programming bottom halves is actually not that easy. So sometimes we may want to execute regular kernel code and then look at bottom halves separately when we have the time. So in terms of interrupt protection levels, there are different kinds of interrupts and there are different kinds of codes that are non-preemptible, where we explicitly disable interrupts. So the idea is that we will arrange them in increasing order of priority, and each level may be interrupted by code running at a higher level, but not by code running at a lower level. So this basically means that user mode programs can be preempted by kernel mode programs. Kernel mode routines, which are more of a bookkeeping nature, can be interrupted by interrupt handlers, because as I have said, interrupt handlers generate their own interrupts because they often need to execute and they often need to interact with hardware. So they, in a certain sense, have a higher priority. So they would preempt normal kernel code. And the ones with the highest priority are top half interrupt handlers, because they need to immediately address the issue with a hardware device. Now, coming to symmetric multiprocessing, where Linux was completely ported to multiprocessor hardware, which is after version 2, regular spin locks and regular locking structures, as we have seen, were introduced into the kernel code, and interrupt disabling no more became the primary method of executing sensitive pieces of kernel code. So, of course, then approaches were made more scalable by splitting a single lock into multiple locks, where each one protects a small subset of kernel data structures. So, with this fine grained locking, so incidentally, locking is still identified as one of the main reasons for the subdued performance of a kernel, not just the Linux kernel, but any kernel. So, fine grained locking is clearly something which is being looked at big time. And then, of course, specific hints can be given to the scheduler with regards to processor affinity. Processor affinity basically means that we tie a given thread to a given processor, and also hints regarding load balancing. So now we have finished the first part of our uh, discussion, which was basically on the history and development of Linux and also on the CPU specific aspects. So next we will start from this slide, which is slide 32, on memory management. So we'll discuss all that Linux does in memory management, IO, and storage management.